Hello everyone, and welcome to the OneClass channel. My name is Jeff Kraus, and today I'm going to run through, I have a PhD in chemistry, and today I'm going to run through a few undergraduate, lower undergraduate level, upper high school level chemistry questions. Today I'm going to make it a little bit more specific. So today I'm going to run through all acid-base type questions. So here's the first one. So in a titration of HCl and ammonia, HCl and ammonia, what is the chemical equation which describes the titration? So in this case, we have a strong acid. Pretty much all hydrogen halides are strong acids except for HF. And this guy's a weak base. The only reason this matters is because a strong acid we will always consider as a species that completely dissociates or completely reacts. So that means the arrow we draw is just one way. And so the entirety of HCl will give us our H3O plus and Cl minus ions. So that means that in the end what we have is NH3 reacting with H3O plus. In our usual double arrow scenario to give us NH4 plus plus H2O. And so that's the titration goes until we match our H3O plus concentration that arises from HCl. But of course, NH4 plus is itself an acid. And so you would also have this equilibrium going on, which is, I guess, partially described by this. And so, but in the end, because you're forming an acid, you at equilibrium or at your equivalence point, i.e. when your NH3 equals your original HCl that you've put in, you should still be slightly acidic because you're forming an acid. Okay. NH3 plus H3O plus, yeah. Yeah, so we've got a strong acid and a weak base, so we'll have a slightly acidic solution. And so that looks good. Okay, for the next one, what is the pH of a 0.1 molar solution of HCl? So again, HCl is a strong acid. So we assume that we get complete dissociation. That means that if we have 0.1 molar initially, then we assume it completely dissociates, giving us 0.1 molar of each of the product ions. So that means as pH is the negative logarithm of our H3O plus concentration, then it's the negative logarithm of 0.1 molar, or you can't put units in with a log, so negative logarithm of 0.1, which is just 1. So in this case, our pH will just be 1. So if we check our solution here, it's strong acid, completely dissociates. That's our pH. So our concentration is just 0.1 molar for H3O plus. And so we take the negative log and we get 1. Okay. And that looks good. Okay. Oxalic acid, if 0.147 grams of oxalic acid dihydrate is neutralized by 23.64 of sodium hydroxide, what is the molar concentration of the NaOH? Okay, so our oxalic acid is going to dissolve into the solution, and if we add it with water, is going to give us HC2O4 minus plus H3O plus. I'm just gonna scroll that down a little bit. But it's a diprotic acid. Yeah, so that's given in the questions. So it's a diprotic acid. So then we also have HC2O4 minus going to C2O4 2 minus, and I'll just add these. Okay, and plus H3O plus. Okay, and then for our NaOH solution, we NaOH is a strong base, so NaOH is going to completely dissociate into Na plus OH minus. And now, if we go through and sum up, we would want to sum it up, but we're producing 2 moles of H3O plus and only 1 mole of OH minus, so that's not going to neutralize. So we would want 2 times this, or 2 NaOH goes to 2 Na plus 2 OH minus. And so we can go through and sum up our full reaction here and get H2C2O4 aqueous. And I'm just going to write the reactant side right now, so plus H2O4 minus plus 2H2O liquid aqueous. I missed the C2 here, so I'm just gonna erase just so I don't make it too messy. HC2O4 and 2 NaOH. So that's the reactant side, and then the product side is going to be HC2O4 minus plus C2O4 2 minus get 2 H3O pluses, 2 OH minuses, and 2 Na pluses. Now, our H3O plus and OH minus are going to combine to give us 4 waters. So that's 4 H2O. Okay. And also we should cancel all things that are the same on both sides. So that will go. And we can cancel 2 of these waters. And so then in the end, we're going to have H2C2O4 plus 2 NaOH gives us C2O4 2 minus. That would be solid. Plus 2 Na plus 2 H2O. Okay, so so that would be the final chemical equation. Okay, and so now, so that would be in solution. I suppose we could use the dihydrate notation as well, and so it would just as similarly be H2C2O4 2H2O. And this is going to, but this will go to C2O4 2 minus plus 2 Na plus 4 water in this case. But as water is our solvent, having 4 water on the right doesn't really change the water concentration. Okay, so that would be our balanced chemical equation. And so getting back to the question, if we have 0.147 grams of our oxalic acid, and it's neutralized by 23.64 mils of sodium hydroxide, what is the molar concentration? So our mass, that's our volume. Our molar mass in this case is 126.07. Okay. And so, and we have a volume of NaOH that's added to completely balance this, or to give us a neutral solution. So first we need to find the number of moles of our oxalic acid that we've added. So that would be the mass over the molar mass, which would be 0.147 grams over 126.07 grams per mole. And if we run this through our calculator, we get 1.166 times 10 to the minus 3 moles. Okay, and then so if we look at our balanced equation, it takes 2 moles of NaOH per 1 mole of our oxalic acid. So that means that the number of moles of our NaOH is twice that is 2 times this value that we just calculated. So that would be 2 times 1.166, which is 2.332 times 10 to the minus 3 moles. So our volume that we've added is the 23.64, and so it wants to know what the concentration is, and so that's just the number of moles over the volume. And concentration is typically in moles per liter, so we'll want to convert our mils here. So it's 1,000 milliliters per liter, and then if we do it this way, the mils cancel, so that means that's the correct way. And so we get 9.86 times 10 to the minus 2 moles per liter. Or in units that are more typically seen, 9.86 times 10 to the minus 2 molar. Okay. So if we check through our solution here, get the number of moles, it's double that, so 2.332. Divide by the volume with the proper unit conversion, and we get 0.0986 molar, or 9.86 times 10 to the minus 2. So that looks good. And yeah, if we check our balanced chemical equation, it's the same. The only thing is he joined the sodium with the C2O4, which is fine. And I guess there's a 2 missing on the NaOH, but it's being taken into account down here. So I think that's just a mistake. 2 is missing NaOH in balanced equation. So I'll just put that there. Okay. Okay, is NH4 plus an acid or a base? So NH4 plus can readily donate a hydrogen ion. So it's a Bronsted-Lowry acid. As it readily donates a hydrogen atom. So NH4 plus H2O can give us, I'm just going to erase that dot because that was a mistake. Can readily give us, or not necessarily completely, it will be in equilibrium. But it can donate a proton to give us H3O plus, and therefore is acidic. Okay, one of the most common ways. So Bronsted-Lowry is one of the easiest to pick out because it's any compound that can readily donate an H plus, especially if it's positively charged. Then you know that it is more likely, at least, to donate the hydrogen. So this looks good. Good. Okay. Now, is CO2 an acid or a base? So for carbon dioxide, it's a bit more tricky, as there are no obvious hydrogens to donate and no obvious OH minus to produce, or anywhere really even to accept an H plus. CO2 is considered an acid. This is mostly because if you bubble CO2 through water, then you get carbonic acid, which definitely does have an H plus that can be donated. And so if you bubble carbon dioxide in water, it will lower the pH, so you'll get an acidic pH. But on top of that, for just carbon dioxide itself, oxygen atoms are quite highly electronegative, whereas carbon is not. So the electron density within the molecule is going to be favored at the oxygen end. So that's what I mean by these little delta negatives, is that the molecule will be more negatively charged at the ends than at the center. The delta just signifies that it's small, so it's less than an electron's charge, but it's present. So what that means is in reactions like this one, where you have it reacting with a heavily negatively charged, in this case atom, or a molecule, then carbon dioxide will act as an electron acceptor, which makes it a Lewis acid, right? So if it acts as an electron acceptor, then it's acting as a Lewis acid, and so then the product of this reaction would be CO. Okay, and so then that would be minus, because there's 7 electrons around oxygen in both cases, so those are negatively charged. The carbon here is still neutral, and this oxygen is also neutral. And so this is the carbonate anion, or a CO3 2 minus. As you can see, the charge is balanced, so that looks good. And yes, so in this case, CO2 is acting as a Lewis acid. So when reacted with anions, it will act as a Lewis acid. And so carbon dioxide is an acid, or a C is an acid. So carbon dioxide is considered a Lewis acid because it can accept electrons from electron donors, as in the example I showed here. And it only completely becomes an acid when you've dissolved it in water and forms carbonic acid. So that looks good. Okay. All right, so now we've got a salt, NH4 NO3 is a salt, and so this is going to dissociate in solution into NH4 plus NO3 minus. To determine whether a salt is an acid or a base, there's some rules, but mostly I'm going to kind of show these rules as I go through a little bit. But if we just look at it, right, we've got NH4 plus, which will act as an acid to give us NH3 plus H3O plus. and then NO3 minus, we would expect it to act as a base to HNO3 plus OH minus. Now, in this case, this is going to take some recognition or memorization a bit. But in this case, this is nitric acid, which is a strong acid. So that means that we actually made a mistake here. The equilibrium does not, there is no equilibrium. This is a strong acid, so it just goes this way. So that means when we dissolve this, salt in solution, that this reaction just doesn't happen. So this one doesn't happen. Maybe I should have circled that. This one just doesn't happen. And this one is then the only one that does happen, which gives us H3O plus. Therefore, this salt will be acidic. Right, so just to reiterate, right, we're going to dissolve this salt in solution, ending up with NH4 plus and NO3 minus. NH4 plus is a strong enough acid to give us H3O plus, but NO3 minus is essentially not a base at all because its conjugate acid is a strong acid. So in this case, the salt solution will be acidic because we've got a stronger acid than NH4 plus is a stronger acid than NO3 minus is a base. Okay, so it's an acid or the solution's acidic. So we have an H plus donor. Yeah, so I'll say the solution is correct. So they pointed out that there was H plus transfer potential from H4 plus, but also NO3 minus is the conjugate base of a strong acid. So must be so NH4 plus is the only reaction, I guess. Just to mention that the existence of NO3 minus, because in this solution they're just using the fact there's no OH minus, but that's not true all the time. It's just in this case because NO3 minus is the conjugate base of a strong acid. Okay, so now I'm going to continue through quite a few of these salts. There's 7 in total, but we can't see all of them here, but I'll preface by saying what the salt is in each case. So, and instead of using the 1, 2, 3 numbers, I'm just going to use A, so I don't get myself confused. Okay, so the first one is NH4Br. This is going to completely dissociate into NH4 plus Br minus. NH4 plus is an acid, or it's a weak enough acid that we're going to get H3O plus. Br minus, if we try to write an equilibrium expression, is going to be HBr plus OH minus, but HBr is a strong acid, so this is wrong, and this only goes in that direction. And so because this reaction doesn't occur, then the solution is acidic. Okay, yeah. So this salt is an acidic salt. And now we can start to see a little bit of what the rules are here. So this salt is formed from a weak base, right? So NH3 would have been the base and a strong acid. So HBr would have been the acid. And so it's a weak base with a strong acid, and so the solution is acidic. Okay? So that would have been its original formation. I find it easier to just look at exactly what's going to be in the solution and work it out that way, but it's up to you. You can memorize some of these rules. Okay, so for B, we have strontium Br2 strontium bromide. So we would completely dissociate into Sr plus Br minus, two of them. Sr plus is going to presumably react with water to give us SrOH minus plus, what's the best way for me to write this actually? How did I write this here? Plus H plus, I guess. That one's a funny one. Yeah. Okay. And then Br minus plus H2O is going to give us HBr plus, that wouldn't be minus, plus OH minus, like that. So I suppose, so that would be the acid and the base in this case, but if we look, right, this here is a strong base, and this here is a strong acid, meaning that these don't occur because they're both going to want to just go this way, and so neither of these reactions are actually going to happen, and so the whole thing's going to be neutral, because in the end all we're going to have is the strontium. We're just going to have the reactant side here, and so if that's in solution, then that's neutral. Okay. So here we have KCN, which is going to completely dissociate to give us our K plus Cn minus. K plus is also just going to give us our KOH, and Cn minus is going to give us HCN plus OH minus. Now again, so as before, this is a strong base, and so this reaction doesn't occur. It actually just goes this way, and so the only reaction that's going to occur is this one, which gives us OH minus in solution, so this is going to be basic. And so we've got, so this is from a strong base. this is from a weak acid, and so the salt is basic. In the question before, I didn't mention it, but they were both from strong acid and strong base, so it comes out to be neutral. So the fourth one here, D, is LiF, which is going to completely dissociate into Li plus F minus. Our reactions here now are going to be LiOH plus H plus F minus. It's going to be HF plus OH minus. Now, this here is a strong base, and so it might start to become obvious, but basically all the alkali or alkaline earth metals with OH are always strong bases, because they will completely dissociate in solution, and so that doesn't happen. It just goes this way. HF is our only hydrogen halide that is a weak acid, so this reaction does occur, and so the salt will be basic. And so again, we have this is from a strong base, which is LiOH. This is from a weak acid, which is HF. So this salt is formed from a weak acid and a strong base, so it's basic. Or we can just write out the chemical equations. So the fifth one here, which I'm calling E, is NH4Cn. Now this is going to give us NH4 plus Cn minus. So in solution we have NH4 plus H2O, giving us NH3 plus H3O plus, Cn minus plus H2O, giving us HCN plus OH minus. So now in this case, we both have a weak acid and a weak base, so we can't make these assumptions that we made above. But depending on which direction you want to see it as, but basically looking at the backwards direction is sometimes easier. But HCN is a weaker acid versus NH4 plus. Okay. So if HCN is a weaker acid than NH4 plus, then that means that Cn minus is a stronger base. Then NH4 plus is an acid. Okay, so stronger base than NH4 plus is an acid, and so then the whole thing will be basic. Now just to add a little bit to that, right? So remember that our KB is always related to our Kw over our Ka, where this is a constant, right? That's the water constant, so 1 times 10 to the minus 14. Ka corresponds to the conjugate acid, so HCN, and Kb corresponds to Cn minus in this case. So that means if HCN is weaker than H4 plus, then this value is very small. If you divide by a small number, then you get a larger number on the other side. So if HCN is a weaker acid than an H4 plus, it means that Cn minus is a stronger base than an H4 plus is an acid, and therefore the solution will be basic. Okay, so I hope that makes sense. Okay, now moving on-ish. So the sixth one, which I'm labeling F, NH4 ClO4 is going to completely dissociate into NH4 plus ClO4 minus. So we've got NH4 plus H2O giving us NH3 plus H3O plus ClO4 minus plus H2O goes to HClO4 plus H2O. Sorry, not H2O, OH minus. Okay, so again, neither of these are strong acids or strong bases, so we can't make any judgments that way. But we can say that this species is a stronger acid than an H4 plus. Okay, so the reason we can say that is because although NH4 plus has a positive charge, this guy is bound to a large amount of electronegative atoms. So it's very likely that this bond in this molecule is very weak. And so this species is going to be a stronger acid than H4 plus, meaning that this species is a weaker base than NH4 plus is an acid. Then NH4 plus is an acid. Okay, so that means if this is a weaker base than this is an acid, then the whole solution will be acidic. So the whole solution is acidic. Okay, and I guess I should have written that somewhere. Oh, I did there, I guess. Okay. Okay. So it was very similar rationales to the previous question, right? Or to the previous salt, because it's just in competition between the acid and base, and as the acid is stronger, then the whole solution is acidic. Okay, and then the final salt is LiNO3, which completely dissociates into Li plus NO3 minus. Here we have Li plus H2O going to LiOH plus H plus, NO3 minus goes to HNO3 plus OH minus. And then if we look, this is a strong base. And this is a strong acid. So this is nitric acid. So this is kind of one of the polyatomics that would be worth remembering. And so then neither of these occur. And so then the whole solution will be neutral. Okay. So, there's, I ran through a bunch of them there. Hopefully it made some sense. So let's check through our solution here. So the first one is acidic, looks good. The second one is neutral because they're both strong acid, strong base. The third one will be basic. The fourth one will be basic. The fifth one, which was the competition between the two, is basic. The sixth one, which again is a competition. Oh, maybe not. Yeah. Oh, okay. So yeah, HClO4 is actually a strong acid. I knew it was a stronger acid, but it's actually just a strong acid. So that's my mistake. So apparently this doesn't occur at all. So that makes that rationale even easier. So that's going to be acidic. And then for the seventh one, it's just neither of them are going to occur, so it's just neutral. All right, sounds good. So that looks good. Okay. Ammonia has a pKa of 38 and acetone has a pKa of 19.2. Will the following reaction take place to a significant extent? Okay, so, oops. All right, so the reaction is acetone. And they've got the structure drawn, but I'm probably going to convert it into something a little bit more readily written out. But I'm just going to bring this all down. Na plus. All right, so that's the way they've written out the question, is does that occur? So H3C2CO plus Na plus actually, I'm just going to get rid of the Na pluses because they're floating around on both sides. And that kind of just makes things more tricky. So it's really asking, does this occur? Okay. So if we look at this, right, so acetone, it says acetone has a pKa of 19.2. So just writing out what this is saying to us. H2O plus, plus H2O, no plus, goes to ammonia and acetone. Okay. yeah, okay, what am I thinking? All right, CO minus plus H3O plus, and NH3, so it's giving us our NH3, so it's giving us the acid constant for ammonia, not the base constant. So that means we're going to NH2 minus plus H3O plus. And so if we look at our equilibrium expressions here, right, our K here is H3O plus, CH3, CH2, CO minus, over H3C2, CO. And our K expression here, I shouldn't do that. So I'm just going to leave this like this, and I'm just going to say, so that's for acetone. So our K for our NH3 is H3O plus, NH2 minus, over NH3. And so that's really the pKa that's being given there, right? So our pKa is the negative logarithm of our KNH3, and our pKa, or pK as it's given in the question there, is the negative logarithm of this K acetone. Okay, so just to write out exactly what we're being given. Okay, so now we want to get this reaction. Right? And so if we look at the two reactions I've drawn, it's really the reverse of this guy, right? So let's write that out. And I'm going to copy down my acetone reaction as well, just because I want it there. Okay. And now I'm just going to write out the reversed ammonia reaction. And so now we can sum these two. And so our H3O pluses will cancel and our H2Os will cancel. And that will give us our reaction that we're interested in. Okay. Now we had the K constant for this guy, right? The K for this will actually be 1 over the K for NH3. Now we'd be tempted to use Kb, as NH2 minus is the conjugate base of NH3. But remember that the Kb value is for the reaction of NH2 minus with water to form OH minus. It isn't the reverse reaction, which is what this is. Okay? And so if we look now, or if you recall, summing a reaction, the K will be just the product. So it will just be K acetone over KNH3. We could also verify that by taking these two expressions here and directly multiplying acetone by 1 over, and you see that your H3O plus will cancel, and you'll end up with an H3 upstairs and an H2 minus on the denominator, which is exactly what we would expect here, right? So it should be products over reactants. Right, so if we take this product like this, then we get exactly these concentrations, which is our K constant. So now if we want our pK for our reaction, it's just the negative logarithm of K acetone over K NH3. Using log rules, we can turn this into a negative logarithm of K acetone minus, keeping the negative sign up front, so it'll be plus the logarithm of KNH3. This is just our pK, and this is just the negative of our pKa. And so then this equals oh yeah, okay, that makes sense. This equals 19.2 minus 38, values given in the question, which comes out to be negative 18.8. So that means the pK for our total reaction is negative 18.8, which means, as it's deeply negative, that the reaction is heavily favored. We can also verify this by saying pK is the negative logarithm of our K, right? And so the logarithm of our K, the negative logarithm of our K is negative 18.8. So our K, canceling the negatives on both sides, is 10 to the power of 18.8. So that's going to be a huge number. Remember, our K is the concentration of our products over the concentration of our reactants. So if it's a really huge number, that means our products are dominating. And so that means, yes, this does go towards products, and it goes towards products quite heavily. Okay, so I hope you followed the logic there. Okay, so let's see here. The pK essentially tells you how much the acid will dissociate. If it's low, then more will dissociate, so you want a lower number. The stronger the acid, the lower. Okay, if the difference between an acid, actually is about 10, it is useful to consider there, but it's greater than 10, becomes irreversible. The reaction between ammonia and acetone will occur irreversibly. Okay, so that's true. I suppose they just straight up took the difference and came up with that. Okay, I will say the solution is correct. Could use much more description to show exactly why. Well, I hope I gave plenty of description there, and my steps were easily followed. So I will say it is technically correct. Okay, so I'm gonna stop that there. And say that's all my questions for today. If you enjoyed it, please subscribe to the OneClass channel. If you want to add questions, please follow the link below the videos. This has been Jeff Krause for OneClass, and